Okay, guys, so we'll start the PCD now. Okay, so problem A is basically like they have given us a password and we have to check all the conditions given over there and ensure that the password matches all those conditions. Okay, so what are the conditions over there? So the password should only contain lowercase English letters and digits. So it can contain 0 to 9 and A to Z in lowercase. And there should be no digit that comes after a letter. So basically, there should be some digits at the beginning, and after that, some letters. There can be some letter and then a digit, and then again a letter or any other thing. Like there should be digits, then letters. There can't be any digit after letter. So that's another condition that you have to ensure is satisfied. Then all the digits need to be sorted in non-decreasing order. That means like digits have to be like 0 to 9 in ascending order. It can't be shuffled in any way, and the letter should also be in ascending order. So these are the conditions that we need to check. So basically, this like it's just a boring implementation problem. So you could do it in multiple ways. So what I did was I kept track of a character known as pre. One second, I think it is very bad. So what I did was I like kept track of a variable known as pre, and what it does is it will keep track of the previous letter, and we'll just check the current letter with respect to this letter and manipulate things accordingly. So initially I initialize pre to be equal to 0, and then what I do is one sec. Yeah, okay. So what I do is initially I set pre is equal to 0. So this is like the base case. Okay. So before inputting any characters, I set pre is equal to 0 and I loop through each character for string is the variable that we are inputting. So I loop through each character, and if the previous character is a number and the current character is a letter, we can continue. Okay, so pre is a number and current is a letter, we can continue, no problem. And yeah, otherwise, if pre is a number and if pre is a letter and the E is a number, okay, so pre is a letter and E is a number, it invalidates one of the conditions, it violates one of the conditions. So in this case, we can print no. Okay, in this case, we can print no. So yeah, and after that, another condition to check is if so this implies this both are either letters or both are either numbers. So we have to check whether pre is less than or equal to E. Okay, so we checking both these conditions will imply that both are either letters or both are either numbers. It can't be like one is a letter or one is a number, because either of these would have been satisfied in that case. So we'll just check whether pre is less than or equal to E. If this is true, we can continue. Otherwise, we can print no over here. Okay, if this is not true, we can print no, and then we again set pre is equal to E at the end of the iteration, because from the next case we need pre to be the current letter when we are processing the next letter. And if it no is never printed, finally we can print yes. Okay, this is basically the way to code this up. This is quite a simple problem. I'll just show my code for this problem. One second. So this is basically my code. So just a couple of lines of template. So this for I comma j comma k, it will basically do a loops. I starts at j and it loops till k minus 1. That's what this loop basically is. And f range I comma j is I starts at 0 and loops up to j minus 1. That's what f range I comma j is. Okay. So yeah, I input the number of test cases and I also input the string and I loop through each character. So just like I told previously, I set pre
Sir,
0. Yeah.
so the code is not visible.
Okay, 1 second. I'll maybe open the code. Okay, 1 second. I'll just share. Code process. Okay, I'll just share that screen instead. Is the code visible now? Hope it's okay, cool. So yeah, basically what I'm doing is I'm inputting the it's not visible like Rajat Sharma, it's not visible yet, the code. You said no. Okay, it's visible. Okay. So what we are doing is we are inputting the number of test cases t, and you're also looping from, and then we are inputting n and the string, and just like I told before, we are setting pre is equal to 0 initially, and done is a variable to keep track of whether so far any condition is violated. Okay, so initially no condition is violated, so done is set to true at the beginning. Then just like I told before, we are checking whether pre is an integer, so is 3 in the range 0 to 9. That's what we are checking over here. And then if E is a letter, okay, if E is in a lowercase alphabet, both these conditions are checked over here. If this is true, we can continue. There is no problem. Otherwise, what we'll check is if A is if pre is a letter and E is an integer. If both of these conditions are satisfied, that means that one of the conditions is violated. So we set done is equal to false, and we can continue. Okay. So after this, what we'll do is we'll check whether pre is greater than E. In this case, the condition where the numbers should be in increasing order and the letter should be in increasing order is violated. So in this case, we'll set done is equal to false, and we can break over here because done is set equal to false. Otherwise, we can just continue to the next iteration, setting pre is equal to E and continuing. If done is true through all the iterations, that means no condition is violated. So we'll see out yes over here. Otherwise, that means one of the conditions is violated. So we'll see out no over there. Okay. So that's basically the way to solve this problem. And yeah, I hope there are no questions so far. We can move on to the next problem then.
Bhaiya, I have a better code than this.
What? Yeah, what's your query?
बस एक बार चेक करना है कि अगर सॉर्टेड है तो यस, नहीं है तो नो.
Can you ask in English, please?
If the string is sorted, then
Yeah.
print yes, and if no, not sorted, then print no.
No, that won't work because you also should check for the condition whether all of them are letters, right? So all of them are integers, right? If they are not integers, the like just checking that, I don't think that will work. Okay, so but
No, it works.
okay, so I suppose what happens, so that the reason why that works is the ASCII values of the integers are also
Yes.
okay. So I wasn't entirely sure about that, so I just wrote all these conditions and checked it. So if the ASCII values are less for integers, then yeah, okay, is sorted would be working.
हाँ.
So yeah, we'll move on to the next problem then. I'll share the problem screen. I hope the problems are visible now. I'll move on to the next one. Problem is invisible. Feel free to check. Say in the chat. Okay, cool. So what is the next problem? In the next problem, we are given two arrays, A and B. A is of length n and B is of length n plus 1. Okay. So these are the two arrays given over there. In this, what we'd have to do is you'd have to like find a way to, you are allowed to do two operations, three operations actually. So you can increment each element of A by 1, or you can decrement each element of A by 1, or you can choose any element of A, copy it and append it to the end. So these are the three operations that they're allowing. Okay, so yeah, you don't need to perform all of these operations. You can perform any operation any number of times in any different ways. Okay, so these are the conditions over there. So basically, this means that since B is of length n plus 1, you would have to perform the last operation once. That's an essential thing. And these two operations you would perform like depending, these two operations are the things that you need to minimize. You need to find a way to minimize this and find the minimum number of operations such that you'll get the final correct output. Okay, so that's basically the way to solve this. So that's basically the problem statement. So how do you solve this? Okay, let's go to the whiteboard. Okay, so to solve this problem, what you need to do is let's say you have to, let's just take one of the sample test cases. Let's take the fourth sample test case. So A is 4, A is basically 4, 2, 1, 2, and what is B? B is 2, 1, 5, 2, 3. Okay, B is 2, 1, 5, 2, 3. Okay, so these are the arrays we have. So what we do is what I did while coding this up is initially I inputted A entirely in one array. Okay, so I inputted A entirely in one array. So this is equal to A, and B, I inputted the first n elements of B in another array. Okay, so B is equal to this. The last element of B, I stored it separately and called it X. So 3, we'll call 3X and store it separately. We'll not have it in the these two arrays initially. Okay. So what we do is we loop through each of these elements one by one. Okay. So while looping through each of the elements one by one, we'll also keep track of another variable initially. So V. Okay. This is the number of so we have two variables. Okay. We'll set V initially to infinity. Okay, V is set initially to infinity, and total is the total number of operations that are required to be performed. And so total, we'll set total initially to 0. So these are the two things that we need to initialize. So what V represents is, V represents the minimum number of ways to get one of these A's. Okay, one of these A's to 3. Okay, the minimum number of steps to required to get one of these A's to 3. Ideally, what we need is we need to find a way to get one of these A's to 3 all on the way of getting it to 2. Okay, on the way of getting it to the value corresponding to it in B. So over here, what I mean by that is, over here, this first element of A, while getting it to B, first we'll reduce this 4 to 3. After that, we'll again reduce this 4 to 2. So we'll need to perform 2 decrement operators on this first element. After performing the first decrement operator, we get 3 over there. In that situation, what you could do is you could copy this element and immediately push it to the end. So this way, we don't need to perform any extra operations to get 3 in the last position. We could just this is the second problem, which is B. We are solving B. So yeah. So on the way of getting 4 to 2, we could easily move to 3 and 2 and move it to the last position quickly. Okay. So I hope what I told over here makes sense. So what we are trying to do is we are trying to minimize the number of separate steps that we need to get here. So while moving each of these two, so another thing that we need to notice is we obviously need to do the absolute value of the difference between these two, 4 and 2. So we'd obviously need to perform 2 operations to get 4 to 2. And again, we'd obviously need to perform one operation to get from 2 to 1. And we obviously again need to perform 4 operations to get from 1 to 5 and 0 to get from 2 to 2. These are all essential operations that we need to perform. Okay. So after we look at, so these are operations that we need to perform. The only other condition that we need to ensure we are satisfying over there is the way to get 3 over here. So we need to get 3 somewhere from these numbers. Okay. So that's something that we need to get. So how do we get that 3? What we try to do is to get this 3, we are moving forward. So there are multiple ways to get this 3. First way, while we are moving from one element AI to BI, if we visit the last element X, what is X? The last n plus 1 element of B. Okay, that's X. So we are storing that as X. We are already defined it over here. So while moving from AI to BI, if we get X in between, we wouldn't need to perform any extra operations. So if X is between AI and BI, we wouldn't need to perform any extra operations to get 3 at the last position. Whenever we move, so anyways, from getting when we are moving from AI to BI, we would be visiting X in between. So we could just take that over there and append it to the end. So in that case, 0 operations. Otherwise, what we do is we see which of the elements in the array is closest to X. Okay. One of the elements, in this case, it's satisfied that we can easily get this from when we are moving from 4 to 2 or from 1 to 5, we would get 3 at the end. So in this case, it's satisfied easily. But in suppose in some other sample case, there is 2 2 over here and 5 5 over here, we never get 3 over here. So what we do is we see which element is closest to 3 and add the absolute value of that element, the absolute difference of that element and 3 to our final output. Okay, so I'd try to summarize the what we are doing over here now. Okay, so the summary. So we get the first n elements of A and first n elements of B, and then n plus 1 element of uh, B is stored as X. We loop through each element in we loop from 1 to n, accessing each element in A and each element in B, and we add absolute difference of those elements in total. Okay, so absolute difference of AI minus BI. Okay, so this will be added to total. So this symbol represents absolute difference, the curve kind of symbol. Okay, so that's we add that to total. And another thing that we need to check is if X, we are also having V is equal to infinity set initially. So we try to find the minimum value of V that we could possibly get. Okay, so we set if X is between AI and BI, X between AI and BI, what we'll do is we'll set V is equal to 0. Otherwise, what we'll be doing is we'll set V is equal to the minimum of, if V is already 0 from the previous things, that's good, because we are taking minimum over here. We are taking minimum of V, comma, absolute difference of X and AI, and absolute difference of X and BI. So these are the things we are computing, and this would be stored as V. And finally, what we need to output is C out. So we'll be outputting after computing all this for all the indexes, we'd output total plus V, and we'd also need to add an additional one. Why do we need to add this additional one? Because the append operation is a separate operation. The appending one of the elements from here after we get the value X, we'd need to append this to the end. So that's one additional operation. Yes, Mohit can note. Yeah, that's the third operation that we need to perform. So plus 1. So yeah, I hope everyone understood this so far. I'll just showcase my code now. If there are any doubts, feel free to ask it in the chat or unmute and ask. Otherwise, I'll show it in my code right now. Show my code. I'm sharing my code now. So I hope the code is visible now. So yeah, we look at the code for problem B. So yeah, just the template. So it's similar to the last one. We are having the for loops, and This is basically just to input SCD scanf, and then long ints have been defined as LLIs, and vector int is defined as VI in my code. Okay, so that's the template that I'm using over here. And yeah, so I'm calling A V1 over here and B V2 in this code, and I'm inputting all the elements in these two vectors. And after that, we are also as I told before, we are inputting the last element, n plus one element of B as X. Okay, so after I'm inputting that, and I'm initializing, instead of initializing total equal to 0, I'm initializing total equal to 1 over here, because I'm not adding plus 1 in the end. I'm just initializing it to 1 over here, and then we'll continue. And we are adding, as I told before, we are adding the absolute difference between V1I and V2I to total. And another thing that we'll do is we'll this is a setting A to minimum of these two and B to maximum of these two, is just to ensure that we'll just to make sure that this check is easier. Okay, so that's something that we're initializing, and we are checking whether X is the last element of B. We are checking whether X is between A and B. If that is the case, we are setting V is equal to 0. If that is false, what we do is we set V is equal to the minimum of V and the absolute difference of A minus X and B minus X. Okay, so this is just something that I explained earlier. And then what we'd be doing is we are adding, finally, after computing finding the minimum V among all the iterations, we'll add V to the total and we'll output the total. I hope this made sense. If there are any queries so far, feel free to ask in the chat or unmute and ask. Anything is fine. So otherwise, we'll move on to the next problem if there is nothing. Okay, so I hope there are no doubts so far. So we'll just move on to the next one. Okay. Okay, so problem C. What is problem C? In this problem, yeah, okay. In this problem, what we are given is we are given n programmers and m testers. Okay, we need to hire n programmers and m testers, and n and m are two numbers that are given to us, and there are n plus m plus one candidates that are available. So there are one extra candidate along with n plus m. Okay, 1 second. I'll share the problem statement again. I hope it is visible now. So yeah, the problem statement should be visible now. Okay. So there are n plus m plus one candidates that are available. So each of them will arrive one by one. There is one extra candidate, and we need to hire only n plus m of them, and there is one extra candidate. And each of the candidate has two skills: programming skill which is AI, and testing skill which is BI. These are the two skills a candidate has. The skill of the team is the sum of programming skills of all the candidates hired and the sum of the testing skills of the candidates hired. So you hire each candidate for one role, either programming or testing, and that candidate will contribute only that particular skill to the total sum. Okay, so you need to, yeah, so that's the total sum. So candidates arrive to the interview one by one. When a particular candidate arrives, we see whether their programming skill is greater than their uh, testing skill. If their programming skill is greater than their testing skill, we assign them as a programmer. Otherwise, we assign them as a tester. But if the number of programmers is equal to n, we'd anyways assign them as tester. We wouldn't be hiring any more programmers, or vice versa. If the number of testers is equal to m, we'd not hire any more testers. We'd only hire programmers. So even if the testing skill of that particular person is higher, we'd set them as a programmer. We'd not hire them as a tester. So those are the basic things over here. Okay, so I hope the problem statement made sense. If there are any doubts in the problem statement, feel free to ask now. So we move on to the approach to solve this problem now. Seems like there are no doubts in the problem statement. Okay, sure. I'll explain it slowly. Uh, okay. So basically, one person wouldn't arrive in this. Okay, so only n plus m candidates would be arriving. Okay, n plus m candidates would be arriving. So for each candidate who doesn't arrive, what we need to check is what is the sum we get? What is the total skill that we get when each of the candidates don't arrive? Suppose the first candidate doesn't arrive, what is the total sum we get? Suppose the second candidate doesn't arrive, what is the total sum we get? We have to compute each of these and check what is the total, like what is the output that we get for each of these cases. So that's basically what we need to figure out for this problem. So what do we do for this problem? We loop through each of the participants, okay? So what we'd maintain is we'd maintain two sets, set 1 and set 2. What set 1 stores is the indexes of the people, indexes of the candidates who have programming skill greater than testing skill. So set 1 will store indexes of index of better programmers. Set 2 will store indexes of better testers. These are the two things that we'd be storing in these sets. One thing that we'd have to notice is exactly one of these two, either ST1 or ST2 would have their size greater than n or greater than m. Okay, so either ST1 will have size of ST1 is going to be greater than n, size of ST1 is going to be greater than n, or the size of ST2 is going to be greater than m. Either of these two conditions are going to be satisfied, like either of these two is going to be happening. Okay, but it's not possible for both of these to happen, nor is it possible for exactly one of it to happen. Okay, why is this so? Say this is greater than n. Okay, say this is greater than n, say this is n plus 1. This is size of ST1 is greater than n, so this condition is satisfied. But then the total is going to be less than m. If this is n plus 1, since there are n plus m plus 1 candidates, the number size of ST2 is going to be m. Okay, it's not going to be greater than m, so it's going to be m. So only this condition is satisfied. But suppose this condition is not satisfied. This is less than or equal to n. Suppose this is exactly n, then the size of ST2 would be greater than m. So this condition would be satisfied. So either one of these conditions must be satisfied. Okay, so that's one thing that we need to like that's one claim that we'll be making. And okay, starting from here, we'll just assume size of ST1 is what is greater. Size of ST2 is going to be lesser, but the size of ST1 is what is greater. That's something that we'll just assume from now on. If it's the other way around, we can just do the same thing in the opposite direction. So like this doesn't lose any generality. So we just assume this condition is satisfied and the size of ST2 is lesser. What we do is, okay, you don't understand the inequality. What this inequality means is which part of the inequality don't you understand? So what it basically means is we have the size of either of these sets are going to be greater than what. So ST2 is the number of better testers, and we need m testers, right? So we need m testers, and ST1 is the number of ST1 is the index of the number of better programmers. Okay, so and we need n programmers. So either of these are going to be greater than the number that we need. both of these can't be greater, because if both of these are going to be greater, say this is n plus 1 and this is m plus 1, then n plus 1 plus m plus 1 is greater than the number of candidates we'll have. So both of these can't be greater. That is one thing that is easily seen. Okay. And another thing is, both of these can't be less than what we have to. If both of these are less than or equal to what we have to, if both of these are less than or equal to what we have, what would happen is this would be equal to n, less than or equal to n, and this would be less than or equal to m. If both of these conditions are satisfied, the total number of candidates are going to be less than or equal to n plus m. But this is a contradiction from what is given in the problem statement, as the problem statement clearly says that the number of candidates that we have is n plus m plus 1. I hope that made sense, Harsha, you asked in the chat. Okay. So that's basically what I'm claiming with the inequality. So the claim is either one of these things are greater. Either ST1 is greater than n, or ST2 is greater than n, so, greater than m. So I hope it made sense now. Did it make sense? If there is any no, both can't be greater. If both are greater, what would happen is, say both are greater. Say we'll assume this is n plus 1 and this is m plus 1. Okay, so in that case, both are greater. If both are greater, what would happen is the total would be, total exceeds n plus m plus 1. So in the even both can't be greater. Exactly, one would be greater. From now onwards, we'll assume that ST1 is the greater thing. Okay. So that's something that we observe, like just assume now, from now onwards, if SC2 is greater, we'd just swap the things, and the same explanation would work from there. So we'll just assume size of ST1 is greater than n. So that's something that we'll assume and solve the problem from now onwards. So what we do over here is all the elements which are greater than n. Okay, so we pick the first n elements of ST1 and keep it in ST1. Okay, the first n elements. So ST1 stores the indexes of the better programmers in sorted order. So we'll store the indexes of the first n better programmers and keep it in ST1. So the ST1 will only keep the first n better programmers. First, this is what ST1 represents from now onwards. N better prog. Prog is the better for short form of programmers. Okay, so first n better programmers are stored in SC1, and so there will be some extra programmers, n plus 1, n plus 2 till size of SC1. There will be that many extra better programmers. So how do we deal with those programmers? What we do to deal with those programmers is, let's just have a variable known as x, which stores the what? Yeah, they are sorted on the basis of the indexes. They come early. That's what we are sorting them on, Nitin. That's the thing that we are sorting on. First n better programmers. Not on the basis of their skill level, but rather on the indexes. Okay, because the reason why we do this over here is, in the problem statement, it's said that we greedily pick the better programmer or the better tester. Okay, so that's the reason. Okay, then we'll set a variable x. What x stores is, x will store the n plus 1th better programmer. Okay, this is what x is. X will store the n plus 1th better programmer. That's what x stores. And the n plus 2 to n plus till size of ST1, all the remaining programmers will have to be testers instead, because the number of programmers required is filled. So all these extra programmers will become testers. Okay, so all these extra things that we are storing in ST1, will insert them into ST2. Insert into ST2. So n plus 2 till last will be inserted into ST2. Okay. So what does this imply? From this thing, so since we have n better programmers, since we are storing only the n n first programmers, st1 size of st1 would be equal to n, okay, because of what you are having over here. After this, size of st1 would become n. One variable is stored in x, okay, so one value is stored in x. One val is stored one in x. So the remaining m must be stored in st2. Okay, so the remaining m is must be stored in st2. Okay. So Vinay Dubey, I hope you understood the inequality because I explained that inequality twice. Did you understand that inequality that I told before? Okay. So that's good. Okay. Since you understood the inequality, I'll come back here. So what you're doing is after that inequality, we're just assuming without any loss of generality that size of st1 is greater than n. If st2 is greater than m, we can just swap them around and do the same thing in the other way. Okay, so in the other direction. So we are assuming size of st1 is greater than n. After that, what we do is, so st1 will have the indexes of the better programmers sorted in ascending order. So st1 is a set, so it will just ensure that that happens. What we do later is, in st1, we store the first n best programmers will be stored in st1. That's something that we'll be doing. So the first n better programmers will be stored in st1. And the n plus 1 programmer would be stored in the variable x, okay? N plus 1 programmer would be stored in the variable x. What we do with this variable, I'll explain that later. We'll just store that in this variable. And n plus 2 till the last value in st1 will be moved to st2 because they would become no, like Nitin, what it have Nitin, so okay, I'll just come back to your question after explaining it to Vinay Dubey. So yeah, like what you're doing is from n plus 2 to the last one, we are storing it in st2. Okay, so we'll store those n plus 2 to the last best programmer would be stored in st2. Okay, so did you understand what you're doing here, Vinay? Like these 3 points. If you yeah, okay, so yeah, okay, I'll come back to this again after explaining the doubt of Nitin. So yeah, okay, so what Nitin, what st1 stores is, st1 stores the first n programmers who have the programming skill greater than the testing skill. Okay, so st1 stores the st1 stores the first n programmers who have their programming skills better than testing skills. It isn't like their programming skills, like they are better programmers than like n plus 1, n plus 2, and so on. It's just that their programming skill is better than their testing skills. The first n programmers with programming skills better than testing skills. Okay, so that's basically what st1 stores. And yeah, okay. So this is what you're doing over here. N plus 2 to last is stored in st2. What are the things that we get from what we have done so far? Because of only the first n are stored, so the size of st1 is going to be n. That is one thing over there. The extra programmer, n plus 1 programmer is stored in x. Okay. So one value is stored in x. N plus 2 till the last one is moved to st2. Since st1 has n and one is stored in one value is stored in x and all the remaining are stored in st2, this implies that the size of st2 must be m. So we have got a case where a size of st1 is n and the size of st2 is m. Okay, so I hope this made sense. Why the size of the this is n and the size of this is m. Okay, so these are the things that we have now. Okay, so the size of so I hope this has made it sense so far. Yeah, I'll explain the part about x in a minute while we are coming to how we'll handle the cases. Okay, so then what we do is we loop from I to n plus m plus 1. We loop I from loop I from 1 to n plus m plus 1. Another thing we'll also have to take care over here is, so we maintain the total variable, okay? Total variable. So what total stores is, total will store the sum of the programming skills in ST1, okay? So for each index in ST1, we'll store the programming skill in total, and for each index in ST2, we'll store the testing skill in total, okay? Total will contain the sum of the skills of the people in these two sets, okay? That's what total will contain. And okay, after this, what we'll do is we'll loop I from 1 to n plus m plus 1. Okay, we'll be looping I. So I is the index of the candidate who doesn't appear. So I is the index of the candidate who is absent. So what we need to check is, first we check whether I is in ST1. Okay, so if I in ST1. This is what we is the first condition that we need to check. If I is in ST1, what that implies is ST1 will have n minus 1 elements. ST1 will have n minus 1 elements, and ST2 will have m elements. ST2 is going to have m elements. So this x, the extra x that we have is x. That's what we'll do with x exactly, Harsha. So this x that we have, we'll add it to ST1 instead. Okay. After removing this I, we'll add that extra x to ST1. So that would mean that ST1 again has size n. So with this, we can update the total value. So we subtract the programming skill of I from total and add the programming skill of x to total, and then we'd be able to output total. So total would be updated accordingly, and we can update total. Total is updated according to the conditions required over here. The same thing would be checked. The same thing would be done if I is in ST2. So we check whether I is in ST2, and if I is the first, this implies that then we'd have n elements in ST1 and m minus 1 elements in ST2, and we'll remove I from ST2 and insert x to it, and we'll update total similar to what we did previously. Okay, so yeah, that's basically how we handle it. Then the third case that we'd have is I is in neither of these things. So what that implies, if I is in neither one of these things, that implies that I is equal to x. Okay, I is equal to x. In this case, what happens is both ST1 will have n and ST2 will have m. So we can just directly output total. There is no update. So the sets remain the same thing. So we can just update output total without updating it in any way. So I hope what we are doing over here makes sense. So this is basically the solution that we have for this. If there are any doubts, feel free to ask me right now. Otherwise, we'll move on to the code now. Are there any doubts? Nice. Okay. 1 second. Okay. We'll move to the code then. Okay. I hope the coding screen is visible now. Problems. We are printing the total variable TB. So I already told about the total variable that we'll. So what total is? Total maintains the sum of the programming skills in the sum of the programming skills of indexers in ST1 and the sum of the testing skills of testers in ST2. So that's what total maintains. Okay, that total would be outputted after checking each condition. So that's what we are outputting after the conditions. So yeah, we'll move on to the code of problem C. We'd input the number of test cases, and n and m would be inputted, and the vector is initialized. Vector of size n plus m plus 1 is initialized, and we are while solving. Okay, cool, Harsha, nice. Okay, so yeah, we'll input all the requirements to both of the vectors. And after that, we'll SC1 and ST2, just like I told before, is initialized, and total is also initialized. Total is a long, LLI is long, okay, LLI is a long, and total is initialized to 0 initially. And we are looping from 0 to n plus 0 to n plus m. N plus m plus 1 means like we are not including n plus m plus 1. We are looping till n plus m because 0 indexed. I'm having it 0 indexed, so you're not pan indexed. And if the programming skill is greater, I'm inserting it into ST1. Otherwise, if the testing skill is greater, I'm inserting it into ST2. And another thing, so over that, I just told an assumption that we'll just assume from here that a size of ST1 is greater than n to ensure that that is maintained in my code. Okay, so otherwise, if size of SC2 is greater than m, we need to repeat the same thing twice. We need to manage SC2 also. So what I did was, if the size of SC2 is greater than m, I swap n and m. I swap ST1 and ST2, and I swap all of one second. I swap all of the values in the vectors. Okay, that means like it's essentially swapped. The problem is swapped where n and m becomes the testers and programmers are just swapped. Okay, this is just to ensure that SC1 is the thing which has greater size. Okay, SC1 is the one which has greater size. Okay, after this, what am I doing? So as I told before, we need to move all the elements from n plus 2 till the last element in ST2, ST1 to ST2. So till the size of ST1 is greater than n plus 1, I'm moving the last element to ST2. So that's what I'm doing over here. And I'm erasing the last element from ST1. And then again, I'm setting the n plus. So now after this, what will happen is size of ST1 will be n plus 1. So this will have the n plus 1 element will be the last element in ST1. And that is set to be the x is basically the variable x I explained when I was explaining the program. Okay, x is that variable. So x is set to be the n plus 1 element in ST1. Okay, then I'm removing the last element of ST1 from the set. Okay, that's basically what I'll be doing over here. And after that, I'm looping. This is just to set up the total variable, looping through all the indexes in ST1 and adding that to the program. The programming skill of that index is added to total. And I will loop through all the indexes in SC2 and the testing skill of that thing. Testing skill is stored in the second position of this vector. So the testing skill of that thing is added to the total. You mean the pre function that I've used over here? That's what you mean, Nitin. So okay, pre was basically like a STL function. I hope you know how to test like the iterators and sets work. Pre was basically an iterator, like a STL function, which is used to move to the previous iterator. So instead of pointing to the end thing, I'm moving to the previous end points to the like the element which is end is an iterator which points to a position which is after all the elements in the set. So to point to the last element of the set, I need to use pre. That's basically why I'm using pre. Okay, and after that, after this base, this is okay. So total is set up, and yeah, okay, others we could probably use that. So I've never used rbegin, so that's basically why I always do this. So I suppose we could use that too. Okay, Rajat Sharma. I'll discuss till problem D till the next problem. Okay. So what we loop from I from 0 to n plus m, and I is the variable that I is the position that we'll be removing. So if I is in ST1, what we do in that situation is what that implies is the programming skill of I is removed, and the programming skill of the x is the x variable that I had while explaining. So the programming skill of x needs to be added to total. So I'm outputting total plus vec x dot f minus vec I dot f because the programming skill of I needs to be removed. And after that, what another thing that we'll do is if I is present in ST2, we'd check whether vec dot okay, if I is present in ST2, we'd have to remove the tester skill of that particular index, and we'll add the tester skill of x to the total and output it. Otherwise, this implies that I is equal to x. In that case, we don't need to do anything and we can output total directly. So that's basically the code for this problem. If there are any doubts after this, feel free to unmute and ask. The x is the variable x that I explained while doing the code. So X is X. Okay, so X that I had while explaining it over here. So this is what X is. That now are you able to understand? So that's the index of the person who was neither in ST1 nor in ST2. X is basically X, okay, TB. So X that I explained while coding, while explaining the pseudo code in the whiteboard. That's what X is. So yeah, like I suppose you could wait. Could you do it without set? Yeah, I suppose you could do it without set two. You could just use like vectors instead, but I use set over that. The complexity would probably be the same thing. Okay, you can do it in O of n too, but it's essentially the same thing. But it doesn't matter. This is an O of n log n solution. Yeah, so you need to observe that X is the only thing that would be moving around Harsha. So that's the part that you need to make sure that you're maintaining carefully, and you'd move it around to ST1, ST2, and that. Okay. So yeah, I hope everything made sense so far. If there is any doubt in this problem, feel free to unmute and ask. Otherwise, we'll move to problem D now. We'll take. Okay. Okay. So I hope there are no doubts so far. Okay. So we'll move to problem D. What is given in problem D? In problem D, we are given an input which is a regular bracket sequence. What is a regular bracket sequence? A regular bracket sequence is something like this. A sequence which, one second. Okay, sorry. It should be visible now, I guess. So I hope it's visible now. So yeah, in problem D, we are given a perfect bracketed sequence. What is a perfect bracketed sequence? It's something like this. Say you have this sequence. In this sequence, all the pairs of brackets can be matched. Like this can be matched with this can be matched with this bracket, and this can be matched with this. That's what defining this mathematically. What this means is in like mathematical expressions, when we do like board mass rules in like 5th grade or something, what we do is we'll have like brackets over there and insert numbers over here. 1 plus 1 plus 1 plus 1 plus 1 plus 1. In a perfect bracketed sequence, it should be possible to insert numbers such that the expression is proper. There is nothing like no bracket that is remaining and nothing is like stuck over that. That's what a perfect bracketed sequence is. Okay. You're given one such perfected bracket sequence, perfect bracketed sequence over there, and you have to count the number of pairs of indexes L comma R. Okay. So L comma R such that L is less than or equal to R. So this is a range of values, okay? So all the brackets in this range, you're inverting those brackets. What do you mean by inverting? Uh, by inversion, you mean you turn a open bracket into a closed bracket, and a closed bracket is turned into an open bracket. That's what an inversion is. Okay. All the brackets in this range are inverted. After doing this inversion, you have to see whether that sequence is a regular bracketed sequence. Okay, that's something that you need. If it is a regular bracketed sequence, then you can then that is added to a total. Otherwise, that's not added to your total. That's basically what you have to do to solve this problem. You have to find the number of pairs of indexes such that uh, you after some inverting all the brackets, it remains as a regular bracketed sequence. So how do you solve this? Uh, Obviously, the most naive approach that you could immediately think of is n cube approach, where you just simulate it and check whether that's possible, and you the O of n cube approach, and if it's possible, you add 1 to the total. But that would obviously TLE. So yeah. Okay, you want me to give an example? Let's see. Okay, let's take the first test case. First test case is simple, so that would be easier to explain. So in the first test case, you are given a regular bracketed sequence. Okay, so that's what you're given in the first test case. Adarsh, I hope you know what a regular bracketed sequence is, or you understood what I have told so far about regular bracketed sequence.
Yes, yes,
Okay.
I'm aware.
Yeah, okay, cool. That's cool. Okay, so then let's say you choose index L is equal to 1. Okay, L is equal to 2. We'll do 1 indexing, and R is equal to 3. Okay, in one indexing. So then this is the range that you're picking. Okay, these two are the things. Then if you invert these two brackets, what you'd have is open bracket, then close bracket. Then this close bracket will get inverted into an open bracket, and then this open close bracket will remain in close bracket. And this is a regular bracketed sequence, okay? Because this is again a regular bracketed sequence. So this L is equal to 2 and R is equal to 3 is a valid pair. And this is the only valid pair, because if you choose L is equal to 1 and R is equal to 2, then what you'd have? Then what you'd have is you'll have this, this, and this, and this. But this is not a regular bracketed sequence, so that's not a valid thing. So that's the only valid pair for this test case. Okay, that's basically what the problem statement says, and you need to count the number of such L, comma R's. Okay, so after this, how do you solve this? There is one interesting way to represent the regular bracketed sequence. What you do is you compute, you set each open bracket as 1 and each close bracket as -1. Okay, one condition to make it so that a regular bracket sequence is not possible is that the number of closed brackets so far is greater than the number of open brackets. So what I mean by this is, suppose you have one open bracket and you have two closed brackets. Okay, this means that no matter what you have after this, no matter if you have a regular bracket sequence after this, this is an imperfect bracket sequence. Yes, Harsha, exactly. That's what it is. I'll come to that. I'll explain step by step and come to perfect sum is positive part. Okay. So yeah, if there are extra closing brackets than opening brackets, that implies that the current thing is a non-regular bracketed sequence. And another thing is that and finally the number of towards the end, the number of open brackets and closed brackets need to be equal. These are the two required conditions that are needed for it to be a perfect bracketed sequence. I hope the two conditions made sense. The two conditions, I'll just repeat it. So the number of closed brackets should be less than or equal to the number of open brackets in any prefix of the bracketed sequence. Okay, so that's one condition. And in total, the number of open brackets and the number of closed brackets need to be equal. Those are the two required conditions. So
I have a doubt.
yeah.
Like you said in the first question condition that number of closed brackets can be less than the opening brackets.
What do you mean? I don't get what you mean.
Like you said in the first condition that number of closing brackets can be less than or equals to the opening brackets in a regular expression.
Yes.
So like how would like number of less closing brackets is like less than the opening brackets would satisfy the regular expression?
Okay, so I'll just repeat the two conditions. Both of these conditions need to be satisfied. One condition is that in any prefix of this bracketed sequence, the number of closed brackets need to be less than or equal to the number of open brackets. The second condition is that in the entire bracketed sequence, the number of in the entire things. Okay, so the entire bracketed sequence, the number of opening brackets needs to be equal to the number of closing brackets. So these are the two conditions. I hope it made sense now. So
Yes, but I didn't get the less than wala part. Like in the first condition, you said less than can be less than the opening brackets.
okay, so I'll explain it with an example. Okay, I hope that.
Yes, yes, sure.
So let's just say this is the bracket sequence that you have. Okay, in this thing,
Yes.
in this prefix, okay, in this prefix, the number of closing bracket is less than the number of opening brackets. Okay, so in each prefix, it can be less than or equal to. But in the total thing, in the entire thing, it needs to be equal to the opening and the closing needs to be equal to.
Oh, got it. In the prefix, this would be allowed, no?
Each prefix, it needs to be less than or equal to. It can't be
Okay,
greater.
okay.
Ever exceeds, it's going to be false. So, so why are we doing this? Why are we having this +1 -1 representation? This is because it makes it makes this very easy. So what we do is we maintain a prefix sum for the bracket. This is something Harsha already told in the chat. It's good. So what we'll have is we'll maintain a prefix sum for each bracket. So bracket sequence. So how we'd maintain it is, so let's just take this bracket sequence. Okay, okay, I'll take another one. We'll have this as a bracket sequence. So if we convert it into 1 and -1, this would be 1, this would be this would also be 1. Sorry, this would be 1, this would be -1, this would be -1, this would be -1, this would be 1, this would be -1. Okay, so we'll consider the prefix sum of this array. What would be the prefix sum? It's going to be 1, 2, 2 minus 1, 1, 1 minus 1, 0, 0 plus 1, 1, and 0 minus 1 minus 1, 0. This is the prefix sum. What would happen if the closing brackets exceed the number of opening brackets? That would imply the number of ones before this current position would be less than the number of -1s. Okay. Then at that particular position, the value over that place would be a negative value. If there is a negative value in this prefix sum array in any position, that implies that the current bracket sequence is not a regular bracket sequence. If there is no negative one, then that implies that the bracket sequence, if there is no negative value in the entire array, that implies that the first condition is satisfied. Okay, every value needs to be greater than or equal to in prefix sum array, every value needs to be greater than or equal to 0. Okay, I hope this condition made sense. So this would make that the first condition is satisfied. The first condition that I explained before is satisfied. Then the second, another thing to keep in mind is that last value of prefix. Okay, last value of prefix array needs to be equal to 0. The last thing needs to be equal to 0. This is to make sure that the second condition is satisfied. I hope these two conditions made sense, and how we are
Yes.
in the prefix summary. Okay, cool. So it made sense. Okay, how would this help us? What we need to do is, what we do to solve this problem is we loop through each indices and set it to be L. We loop for L from L1 to N. Okay, once again. L1 to N. We fix L. Okay, we are fixing L as one of these indexes. And we need to find the number of R's which satisfy both these conditions. Okay, pref I is equal to 0, pref of the entire array is equal to 0 will be satisfied no matter what, because the sequence that we are given is a regular bracketed sequence. Even after we do the inversions, okay, no, that will not always be satisfied. Sorry, that's just okay. So we need to we are fixing L. L is the index that we'll be inverting. So L is something that we'll fix. Then we need to find the number of R's such that if you're inverting all the brackets in the range L comma R, the entire thing would be a perfect bracketed sequence. So we need to find the number of such R's. So how do we do this? We'd have pref L minus 1. Okay, pref L minus 1 is going to be the prefix sum value of all the elements which are less than or equal to L minus 1. So pref L minus 1 stores the prefix sum values up to L minus 1. So that's something that we have. And what would happen is pref L minus 1 will remain the same. Okay, suppose we are swapping some set of values. Okay, after swapping it, what would happen is those values would have been positive in the those values would be something in the prefix sum array. Okay, so suppose we are setting R is equal to something, let's say R is some value. Okay, and let's set X is equal to prefix some value from L to R. Ref L to R. Okay, the sum of all the values from L to R. That's what X is. Okay. So all these values, so this value would be something. Okay, let's say this value is 5 currently. Okay, let's say X is equal to 5. After inverting all the brackets in this sequence, so the plus ones over here would be minus ones, because the after inverting a bracket, a open would be becoming a closing bracket. So a plus one would be a minus one, and a minus one would be a plus one. So what this would mean is X, which is 5 currently, would become minus 5. Since we are inverting all the brackets in the range L to R, X would become minus 5 after we invert them. Okay, since X becomes minus 5 after inverting all the brackets, we'd have to ensure that pref L minus 1 plus minus 5 plus minus 5 remains positive. Okay, that's something that we need to ensure, because otherwise pref L minus 1 minus 5 needs to be positive. I hope this made sense. Why this is the case.
Yes, got it.
Okay, cool. So pref L minus 1 plus X needs to be greater than or equal to 0. Otherwise, the condition that everything needs to be greater than or equal to 0 will be violated when we are checking from L to R. Okay, so that's basically one thing that we need to check. Another thing that we need to check is, since the sum of all the elements in the thing needs to be positive. Okay, so since the sum of all the elements in the array needs to be positive. Okay, needs to be 0. The number of open brackets needs to be equal to close brackets. The prefix n needs to be 0. But after swapping all the elements L to R, okay, so after swapping all the elements L to R, suppose it becomes 5 over here. Initially, it's going to be 0. Okay, so initially, the thing is going to be 0. But for that, X needs to be 5, because X is equal. But if you are making this entire thing X is equal to minus 5, then what would happen is that entire range, okay, that entire range from 5 it goes to minus 5. What would happen to the sum? The sum of the entire thing. So a particular set of values go from 5 to minus 5, then the sum will decrease by minus 10. So, and the 0, it's not going to be 0. Then that condition is going to be violated. So another thing that we need to check is the prefix sum of L to R is has to be equal to 0. So X needs to be equal to 0. X can't be any other thing. And okay, another thing that I missed while telling over here is while we are checking prefix of L to R, X doesn't like, you don't only check for the like you check for the maximum value over here, not just the sum of the values, the maximum values. Why is that so? Suppose L to R minus L to something between L comma R. Okay, so suppose L is 2 and R is 10. Suppose L to L to 7 gives you a value of 5. Not L to 10 wouldn't give you a value. L to R wouldn't give you a value of 5, because L to R will always be 0 because of this condition. Okay, so this is another condition that we're having. X L to the sum prefix sum from L to R needs to be equal to 0. That's one condition that we have. So the other thing is that we don't only check for the sum of the elements from L to R, but we also check for the maximum of the element maximum sum from L to R. So suppose L to R minus 5 is the maximum thing. L to R minus 5 gives you X is equal to 5, which is the maximum thing. This is what we'll check whether pref L minus 1 minus that value is greater than or equal to 0. That's what we need to check, not the pref L to R sum. Okay, so I hope this made sense what you're doing over here. If it didn't make sense, let me know. I'll repeat it. Did it make sense? If it made sense, feel free to change in the chat. Okay, I hope it made sense. I'll move on to the next part. Okay. So, okay, these are the two conditions that we need to see. For a fixed L, we need to see that when we are having a particular R, there is no value between this L and R such that sum up to that point exceeds pref L minus 1. Okay. Sum from L to that particular thing does not exceed pref of L minus 1. That's one condition that we need to see. The second condition that we need to see is the sum from L to R is equal to 0. That is the second condition that we need to see. So these are the things that we need to count. So how do we do this fast enough? Okay. So how do we do this fast enough is the next question that we have. So to do this fast,
using maps.
yeah, okay. So we'd using maps is to the second condition we'll use maps, okay. But for the first condition, what we need is we need to find the maximum element in this range, okay. So if you find the element such that the sum from L to that particular index exceeds pref of L minus 1, okay, then that implies that we can't take any R after that. We can't take, suppose L2, let's say L is equal to 2 and the sum from 2 to 5 exceeds pref of 1. Segment tree, yeah, Harsha, segment trees could be used, but I use the sparse table over here because I had to do an additional binary search too. So if I use a segment tree, it will become log square. So I was not sure if it would fit the time limit. I'll explain how I did it in a minute. So I'll just explain this additional observation and I'll come to the implementation part. Okay. So what we need to do is from a particular index L, we need to see if there is an index, some index after this L such that the sum from L to that index exceeds the prefix sum of L minus 1. That implies that we can't pick any R after this. Any R after this can't be picked. Okay. R should be only less than this particular thing. Okay. So suppose L to 5 exceeds 2 to 5 exceeds pref of 1. Okay. Prefix sum of 1. That implies that we can't pick anything after 5. Okay. So 5 to something else can't be our R value. That is something that is implied because of this condition. I hope this condition made sense. Why this condition appears. If it didn't make sense, feel free to ask in the chat or in the middle. Okay. I hope it made sense. After that, what we'll have is, so we'd find particular index. Okay. After we find this particular index, we'd only need to check from L to this in. So since at position 5 we exceed that thing, that condition was violated. So we need to check from 2 to 4 alone. From 2 to 4, we need to check whether L to that particular position, the prefix sum to L from that to that particular position is equal to 0. So how to do that? What we'll do is we'll store the for each prefix sum, we'll store the indexes at the positions at which the prefix sum becomes equal to that particular thing. Okay. So for I did this with help of a map. Okay. So for each prefix sum, I store the indexes, and for the L to this thing to be 0, what we'd have is that value over that is going to be equal to pref of L minus 1. So in that map, I checked for the indexes with pref with prefix sum equal to pref L minus 1. I checked the number of indexes with position from L to R. That's the check that I had in my thing, and the number of such positions is added to my total. Okay. So this is how I check the second condition and added to my total. I hope the checking the second condition part made sense. Okay. Now, what we need to, if there is any doubt with how I check the second condition, feel free to ask it in the chat. Now, the only part left is how do we check the first condition? That is, how do we find the first index where pref L to R, the sum of pref L to R exceeds pref L minus 1? How do we find the first index? So one obvious thing that we can see is we do a binary search. Okay, binary search is what we like. Looking at this, it seems like a quick thing that binary search might work because up to this index it's possible, but beyond that index it's not going to be possible. So it's monotonic. So binary search is the first obvious thing. So what do we binary search for? What we'll do is we'll binary search from L to N, the first index, where the maximum value of that thing does not exceed maximum value of that thing such that the sum from this to this does not exceed that thing. Okay. So what do we need? So we need to, for a particular range, we need to find the maximum value. We can't just pick the last value or anything. For a particular range, we need to find the maximum value. To find the maximum value, we can use any range max data structure, either a sparse table. Sparse table does it in O of n, O of 1 time complexity. So that makes that the binary search plus the sparse table complexity remains at O of log n. Otherwise, we could use a segment tree too, but I'm not sure if a segment tree would fit the time limit, but I suppose it should O of a segment tree would make it so that the time complexity would be O of n log square n. And then again, we can use either of these data structures and find the maximum value over there and check whether the prefix sum of that thing, the sum from that thing to this thing does not exceed pref of L minus 1. So the maximum value, the maximum prefix sum till L. Okay, so we find the maximum prefix sum. Let's call that equal to Y. The maximum prefix sum equal to Y, which we find with the range query data structure. And we'll do prefix sum of, so we'll do Y minus pref L minus 1. So what is this? Y minus pref L minus 1 will give us the prefix sum from L till that particular index, whichever index has the maximum prefix sum value. And we'll see whether this is less than or equal to pref L minus 1. This is the condition that needs to be satisfied. Okay. So if this condition is satisfied, the binary search predicate function will return true. Otherwise, it will return false. That's basically what we need to check with this thing. Okay. I hope this may have made sense how we are checking the first condition. So with this check, we'll find the first index which is satisfied. And with that first index, we'll from L to that first index, we'll find the number of positions with value equal to pref L minus 1. So those are the checks that we'll be doing. I hope that made sense. If there are any doubts in this approach, feel free to ask in the chat. So with this, we'll get an O of n log n approach. N log n provided we use a sparse table. If we use a segment tree instead of a sparse table, we'll get an O of n log square n approach. I am not completely sure if there is a simpler approach without a data structure. Okay, I couldn't think of any during the contest. Like if there is a simpler approach, maybe we could look at the editorial and see whether there is a simpler one later. Okay, but I had these two approaches. The complexity of O was O of n log n and O of n log square n if you use a segment tree. I had this complexity in my code. So yeah, now if there are any doubts so far, feel free to ask it in the chat. Otherwise, we'll go to the code. Okay, since no one has any queries so far, I suppose it made sense completely. And yeah, we'll go to the code after this. Okay, this is basically just my sparse table template. This is nothing much. So yeah, in the sparse table query L comma R will return the max element and in that particular range. And yeah, I input the string from the user and convert the string from that Okay, Rajat Sharma, which level are you in currently? And okay, once again, I'll share my code again. Okay, once again, sorry, I'll share my code again. Right. Okay, level 4. I'm not completely sure. I don't know. Like level 4 had data structure things. I'm not sure if it's covered. Otherwise, I'll after the meeting, I'll share some link containing information about sparse table. You can look at that and learn about it. Okay. I'll share something in the TLE Discord server, and yeah, after the meet is over. Okay. So now I'll share it in the Discord server and you can take a look at it and learn about it. Okay, I'll share some good resource for it. Okay, now okay, this is the code. Okay, so this is basically my template for the sparse table, nothing much. So query L comma R will return the maximum element in the range. Okay, so that's the template I had, and I'm inputting the string and converting that string into the prefix sum array that I had earlier. So yeah, I'm converting that into the prefix sum array. And for this is a map with source for each prefix sum, the indexes at which that prefix sum appears. Okay, so this is basically done to check the second condition that I have had while explaining the code. Okay, so that's what this does. And total is initially set to 0. LLI total is initially set to 0. and the vector what I'm doing over here, this is just to initialize the sparse table. These two lines are to initialize the sparse table. Vector is equal to pref and init is equal to n+1. Total is the value that we'll be outputting finally. This will keep track of the number of values that the number of things that we'll get in each iteration, and I'll add that up to total, and I'll finally output that. Okay, that's what total is. And first, what you're doing is we are binary searching for the first index such that binary searching for the index till which we need to check. That's just like what I explained over that. And we are finding the mid value and querying for the maximum value up to that point. And the prefix sum from L to R, L to that maximum prefix sum, is that if that is greater than pref L-1, the condition is violated. If the condition is violated, we can't pick mid. Mid can't be an element that we pick. So high would be set to mid-1. Otherwise, otherwise the condition is not violated. The like basically the predicate function returns true over that. So we'll set low is equal to mid. This is such that the condition is false, and this is the place where the condition is true. If condition is true, we are setting low is equal to mid. Otherwise, high is equal to mid-1. And then we'll set the first index is equal to then basically we are in the map, we are finding the what we are doing over here is we are finding the this is basically, this part is just to find the indexes we are which are between L and the ID we are found over here, the ID up to which we are found over here. So we are finding the number of values which have prefix sum equal to pref L-1 in this range, L to low, in this particular range, the number of values which have prefix sum equal to L-1. That's basically what we are doing, and we are adding that to total. We are adding that particular value to total, and we'll output total. So that's basically what you had having in our code. If you have any doubts in the code, feel free to ask in the chat. And yeah, that's basically it. If you have any general doubts up to this point, feel free to ask now. Otherwise, we'll end the meeting now. Okay. Are there any doubts? Okay, seems like there are no doubts. So I'll end the stop the recording, and I'll end the meeting now. So yeah, thank you guys.
Hello. Hello.
Yeah, hello. Yes, I can hear you.
Actually, I have some doubts in learning the past table.
Which problem?
Okay. Like, like I'm not aware about the past table concept and data structure.
Yeah.
So could you please suggest me some resources or some YouTube channels from where I could learn?
Send it in TLE Eliminators comment chat now. I'll find some good resource. I think USAC Code Guide has one. I'll just find that up and send the link in the comment chat. Rajat Sharma also has the same thing. I'll send it up. You just check it. I'll send it in 5 to 10 minutes after the meeting.
Oh, okay.
Yeah, okay, cool. Okay, I'll end the meeting now. I'll stop the recording.
Sure.